is the following true, that a set intersectioned with itself is just going to be equal to the set itself, or A intersection A is equal to A. So what do we notice here? Well, let's visualize this very quickly. This should be fairly straightforward. It does appear to be true, but if you can't picture why this is true, let's quickly draw a picture, right? So this is our set A, and usually when you have two sets, you want to draw them like this, right? But remember, because A here has to be the same set, this intersecting part, this overlap is what we're interested in, right? So we're just going to highlight that. This is what we're interested in showing is equal to A. But because once I was just saying A is equal to A, they're the same, these two circles actually completely overlap, and this becomes something that looks like this, and you can just draw A over top itself, right? Because you have two A's here. I'll draw like a second A here. And because the intersection is all of it, you're actually highlighting all of this circle. And what do we notice? This entire circle is just our original set A, so that's why this is going to be true. So let's go ahead and prove it. So before we start doing our proof, we have to recognize this is an equality, which means that we need to prove that the left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side. Why? Well, if we can show every element in this set is going to be in this set, and we can show every element in this set is going to be in this set, then they must be the same thing. So what does this mathematically mean? It means we have to prove this statement, and we need to prove this statement. Both of these have to be true in order for us to say that they are in fact equal to each other. So let's go ahead and do that. So to start our proof, we're going to start with a let, because this is actually a for all proof in disguise. Because we don't have any restriction on A can be any set. And when we have the words any or for all sets A, we're doing a for all proof. So this is going to be a for all proof, which means we're going to start it with the word let. And what are we going to let? We're going to let A be a set. There we go. Now we can get into the two cases I mentioned before. Let's start by proving that the left-hand side is a subset of the right-hand side. Okay, so our first case is going to be proving this, and how are we going to do this? Let's sketch our proof. We want to say that this is going to be a subset of this. We're going to start here. We have to show that when you start with this, you can in fact get to our goal, which is going to be showing it's a subset of this. But how are we going to show it's a subset? Well, remember what I said, a subset means every element here must also be an element here. Well, that means that any element X, if I create, let me make some more space maybe here. If I create some arbitrary element X, and this X is going to represent every element in this set, if X can be in A, then they are in fact subsets, right? If X represents everything here, and we can show X is here, well, since everything here is in here, this is a subset of that. That's the logic. So where do we start? Well, let's start by breaking this apart. We're going to say, well, if X is an element of A intersection A, that means that X is an element of A and X is an element of A. That's what this is saying, right? And then from here, how can we get to here? Well, as you can see, the logical leap isn't very big. You can say, well, because both of these are true, and both of them lead to here, well then it means this is true. So there we go. Now that we've shown every element X is in here, is going to be in here, this is a subset of that. So let's go ahead and put that into words. So we start by supposing our theoretical variable X. We're going to say, suppose X is an element of A intersecting with A. Now we want to break it apart. We want to use our sketch. Our next step is going to be to explicitly state that when this is true, that means this is true. So we say, then X is an element of A and X is an element of A. Fantastic. And now what can we say? Well, we can say in both circumstances, X is an element of A. And then because we've shown X is in here and X is in here, we can say this makes, or making A intersect A subset of A. There we go. We've proven our first case. It's a very simple and short proof. Now let's prove our second case. Okay, so how are we going to prove this? Well, we're going to use the same strategy we did before. We're going to sketch this. We're going to say we're starting with A, and we're ending with A intersect A. This is our goal, and we want to get from the start to our goal. we have to show that everything here is going to be here. So we're going to let some element y, I'm going to choose a different element to not confuse the reader, y. Y is going to represent everything in A. And we just want to show that because y is going to be down here and it represents everything, everything is going to be here and here, which makes this a subset of that, right? Exact same logic as in our first case. But how do we get from here to here, right? We can't break this up any further, any more fundamentally. So what we're going to do instead is we're going to actually broaden this. We're going to say, well, this is going to be the same as saying y is an element of A and y is an element of A, right? We're going to do kind of the reverse of what we did in the first case. And the reason we can say this is because when this is true, this still keeps this true, right? When you're making your next statement, you want to make sure everything you've said beforehand still remains true. If we said something like this, y is an A and y is not an A, that would contradict our assumption, so this would not be correct. But because saying this still makes our first statement true, that y is an element of A, we can make this statement. And when we say this, well, you can clearly see that this thing together is the same as saying A intersectioned with A, which then makes y an element of that. So let's put that into mathematical words. Where do we start? We start by creating our element. So we say, suppose y is an element of A. Fantastic. Then we want to not break this up, we want to broaden this. We want to make another statement that's true, but keeps this true. So we're going to say, then y is an element of A and y is an element of A. Fantastic. Or maybe we'll continue the sentence and we'll say, thus, making y an element of A intersect A. So now that we've shown this, we can say because every element y is an A and every element y is an A intersection A, we can say that because of that, so A is going to be a subset of A intersect A. Fantastic. We've proven both of the cases to be true, so now we can conclude that this is going to be true. So let's go ahead and write our conclusion down. We're going to say that since A intersection A is a subset of A, and A is a subset of A intersection with A, then A intersection with A is equal to A. There we go. We have proven that this is in fact true.